Okay, so there's the assignment for Section 4. It's not huge because it's a lot of the same kind of problems that we did in Section 3. You don't have to use Pascal's triangle. What you're responsible for is knowing how to generate Pascal's triangle. Yes? Yeah.
Is that the same one that's on the Excel spreadsheet?
Yeah, should be. Yeah. If it's different, then you can, whatever's on the spreadsheet, whichever one you do is fine. So they're basically the same. So we just got 2 things left to look at in this section. This particular example has applicability to something that we'll do later when we talk about probability. So the question is, we talked about flipping a coin, and if you flip a coin 5 times, there are 2 to the 5th power number of combinations of heads and tails that you can get. So, and we could do a tree diagram. We could just list them and use some kind of pattern, like we did with truth tables, to come up with the listing. And if you actually just list all the different possibilities and then group the ones together that have, in this case, 1 head. So you've got heads as the first toss, heads as the second toss, third, fourth, and 5th toss. So there are 5 out of the 32 are 1 head only. And then you can list all of you don't need to write all this stuff down because it's in your book. So then there's the possibility of 2 heads, and so you can list all those out. And if you count the number of occurrences of 1 head, 2 heads, 3 heads, 4 heads, and 5 heads, and 0 heads, you'll see that it's 1, 5, 10, 10, 5, 1. And if you go back to Pascal's triangle, you will see that the 5th row of Pascal's triangle is 1, 5, 10, 10, 5, 1. And that row represents 5 things taken 0 at a time, 5 things taken 1 at a time, 5 things taken 2 at a time. So it seems like we ought to be able to explain why that's the case. It's not a coincidence. But it's not, it's not our normal combination problem. A normal combination problem would be we've got 5 people and we want to choose 2 people to be on a committee where order is not important. In that case, okay, we understand that. Or we've got 5 things, we've got 5 boxes of stuff and we want to sample 2 of the boxes. How many different how many different subsets of boxes, 2 set boxes could I use? Well, the way you look at it, you just have to think of it in a different way. And so what you're thinking of is instead of like 5 people, you have 5 slots, meaning 1 slot is getting ahead on the first toss, 1 slot is getting the head on the second toss. So instead of having names, you would have first 0 toss, well, first toss, second toss, third toss, fourth toss, and 5th toss. Okay? So so that's what I'm looking at. So I'm choosing which tosses am I going to get 1 head. So all I'm talking about is the heads. The tails come automatically because if I don't get a head, then I'm going to have a tail. So if I say, okay, what are the possible subsets of which toss am I going to get get the head on? So the possibilities are none of the tosses, the first toss, the second toss, the third toss, the fourth toss, the 5th toss. Okay. So I'm picking. So it's just thinking the problem in a different way. Instead of names, it's tosses. So I have an example here on my next page, try to explain it better, what I'm saying here. So instead of people's names, I'm going to say get heads on the first toss is H1, just like letter A would be the representation for a person with a letter A starting their name. Getting heads on the second toss is H2. Heads on the third toss is H3. Getting a heads on the fourth toss is H4. And getting a heads on the fifth toss is H5. So if I say I want to, of these possible places to get a head, I want to pick 2 of those places and group them together. And if I get, so that's the 2 tosses that I get ahead, and the other ones are the ones that I, if I pick, for example, if I say, well, one possibility is to get the head on the first toss and the second toss. What that by default means that I'm going to get a tails on the third toss, the fourth toss, and the fifth toss. If I say I'm going to get a heads on the first toss and the second toss, a third toss, that means the second toss is a tails, the fourth and fifth toss are tails. So it's, and if you do that, these are the possible combinations. It's just like using the case. So I'm going to try to use this as an analogy from what we've done before to show that it's the same concept. Okay, add a page. Okay, so we had five people's names instead of 5 tosses, and the question was, how many 2-person committees could I have? Well, because I'm asking this, because I'm specifically talking about committees, I would say, okay, I've got 5 people, I'm choosing 2. Okay, that would be pretty straightforward. But what I'm really doing here is, and this ends up being, I think, 10. What I'm really doing is I could list all the different committees. I could have person A and person B. I could have person A and person C. I could have person A and person D. I could have person A and person E. I could have, I'm trying to be exactly the same as what I have over here. I could have person B and person C, person B and person D, person B and person E, person C and person D, person C and person E, and person D and person E. So those are my 10 different committees that I could form. I've just listed them out. And I have, here are my different ways of getting 2 heads. I can get it on the first toss and the second toss and so forth. So I'm doing the same thing, even though I'm not really I'm not selecting a committee, or I'm not selecting samples, but by casting the problem in that way, I can think of these, I can convince myself that those are what the results should be. You can use combinations to come up with a way of predicting not only the total number of combinations or the total number of different total number of different arrangements, because the total number would be based upon the fundamental accounting principle, a 5-step process, 2 times 2 times 2 times 2 times 2 times 2. What I'm doing here to find how many out of those 32 are 0 heads, 1 head, 2 heads, 3 heads, 4 heads, 5 heads, I can end up using the combination formula to get the results. Where is this going to come in important later on? It's when you have a process that, well, in probability, which we'll find out in Chapter 11, is usually we have something happening or something not happening. It's what we would call a binomial choice. It's either true or it's false. You're a member, you're either my friend or you're my enemy. That's the political thing. There's no black and white. And there are a lot of things where you can cast it as being true or false, or heads or tails. In this case, it's a 50% probability of getting a heads or a tails. When you flip the coin, if it's a fair coin, half the time you're going to get heads, half the time you're going to get tails. But one of the examples I use in Chapter 11 is shooting free throws. So if anybody plays basketball, if you get to the end of the game and the team is down by 2 points and the guy gets fouled, and it's a 3-point shot, so he gets 3 shots. What's the probability of the team winning based upon the free throw percentage of the person shooting? Well, you don't know because it's all random. You don't know whether he's going to hit 5 out of 5. It's more likely. Pardon me? Yeah. Well, if it's 50% free throw, but if an 80% free throw shooter is going to have a better probability of winning the game for you than a 30%. But how much difference? You can actually do that using probability. So we'll get to that. I think it's cool because I am a good free throw shooter, so I can imagine myself up there like this. Shaq, don't foul. Yeah, Shaq should not be. Yeah, he can't shoot worth any. Okay. So the point you should get out of this is there are going to be instances where we can use the combination formula for things that may not initially seem like combinations. And there's another example right here. I'm not going to ask you to do anything as that complicated, but let me. When it comes to gambling, which we don't endorse in any way, but that was the whole reason for probability. The science of probability initially had to do with gambling. So you had some king, and he paid some mathematician to figure out how to play a game and have the best chance of winning, getting money, or setting odds of the game. And so, you might have the question. Here's an example. How would you calculate the probabilities of the following 5-card poker hands? So what's the probability of randomly dealing 5 cards? What's the probability of you getting a royal flush, which is, I think, the hardest card? Pretty close to, it's not exactly 0, but it's pretty small. What's the probability of getting 4 of a kind? And as you go down, they're more likely, they're more probable, but you don't know what the odds are. People who count cards do know the odds. So let me just show you here how it works. So I'm not going to go into all the details of how you calculate it, but one thing you should notice here in the formulas that they go through is 13 things 1 at a time, 4 things 4 at a time, 48 things 1 at a time. What that product gives you is that out of the total number of possible card hands, there are 624 4-of-a-kind hands. So we'll talk more about this when we get to probability. The reason I bring it up now is to show you that we are using this combination formula for something that, again, doesn't appear to be directly to be a combination problem, but it is. I'm not going to teach you well enough to count cards, but I'm going to at least give you an idea of the different probabilities of different card hands. So if I search on Google for probability of card hands, there should be a poker probability, okay? And if you look at this somewhere down here, they tell you, okay? So here's the royal flush, and there are 4 out of the 2 million different card hands. Yeah. So if you take this number and multiply by 4, which is 2.5 million, there are 4 out of the 2.5 million are royal flushes. So I guess a royal flush is the 10, Jack, Queen, King, Ace of one suit. And there's 4 incidences of that. So to find the probability, you take 4 divided by 2.5 million of all the different hands. And you can see, if you go down, you can see the different probabilities of getting certain card hands. The one I just mentioned was a 4 of a kind. And what this is, so there are 624 different 4 of a kind hands. And so if you take 624 divided by 2.5 million and multiply by 100, it's a 0.0240% chance of getting a 4 of a kind when you initially deal cards. And you go right down to here, one pair is the the chances of getting nothing is about 50%. So if you deal 5 cards, the chances of having nothing, no card hand, not 2 of a kind, 3 of a kind, 4, and all the things, is 50%. That also means that 50% of the time you'll get at least 1 card hand. You'll get something. And it all comes down to these things over here are basically 13 things taken 1 at a time, 4 things taken 2 at a time. These are all combination formulas. Now, probability nowadays is not just for gambling. If you take statistics, there are 2 kinds of statistics. There's descriptive statistics, which is probably what you've seen before, where you calculate a mean and then you calculate a standard deviation and you present the data in some graphical form. The other kind of, does anybody know what the other kind of statistics is besides? What's that? You're about to find out? Yeah. I'm going to tell you. I am. Anybody else know what it's called? It's called inferential statistics. Okay, and that involves probability. So it's very important in that. And so there's descriptive statistics and there's inferential statistics. We're only going to talk about descriptive statistics in this class, but okay, that's a little stuffy. Okay, where are we going here? Section 5. So the last section is counting problems involving not or. So sometimes it's easier to, instead of counting something, it's in one way, it's easier to count it in 2 different ways and use subtraction, subtract one count number from another to get the net result. You'll see how that makes sense in a second. So it's just handling what is, well, we'll give you an example in a second. It's easier. But it usually involves a problem like we've dealt with, but involves the words not or the word or. So this is called the complements principle of counting. Again, this is in your book. The number of ways a certain condition can be satisfied is the total number of possible results minus the number of ways the condition would not be satisfied. Symbolically, if A is any set within the universal set, then the number of, so if you remember back to the first semester, don't worry if you didn't have the first semester. Remember, this was the number of elements in the set. We call that cardinality. So what it's saying is the number of elements in a set A is the number of elements in the universal set, which is the number of total choices, minus the number of elements that are not in the set. So that's how you do it from a set notation standpoint. From a diagram standpoint, let me just put this on 2 pages. So we use these things called Venn diagrams, and the rectangle represents where all of the things that we're taking into consideration we put in there. So in say in our case of our room here, if we put everybody's name somewhere in that rectangle. Now let's say the circle is all the men in this room. Okay, so what we do is we'd write the men's name in here, and we put the women's name on the outside. And so if it looked inside the rectangle, it would be everybody's name. And what they're saying is that if you knew how many total people are in this room, so let's just ask that question. So how many do we have in here? We have 1, 2, 3, we have 6, 9, 11. Okay, so we have 11 people. And we have 1, 2, 3, 3, that's all? 4. So we have 4 women. So the question is, without counting the men, how many do we have? Well, I answered the question. We don't have to count the men, because if we know how many total people we have in the room, and we know how many women we have in the room, and there are only women and men in the room, so only 2 choices, then we don't have to go back and count the men. We just say, well, the number of men is the total number of people minus the number of women, and women are not men. Okay, so that's where the not comes in. So if it's easier to count, if you had 100 people in a room, I've got 100, everybody's sitting in this big auditorium, you got 1,000 people, so there are 1,000 seats. It's a computer programmer's convention, and so rather than counting the amount of men, you'd say, well, it'd be a lot easier to count the amount of women. There's 3, yeah. All the women raise their hands, so you'd have like 3. Okay, so that means we have 997 men. I don't have to count 997 men, so it's easier to count the number that are not and subtract those from the total number to find the number that are. So that's the whole concept here. Okay, so this is a problem in your book. Let me find the numbers so you can reference it. This is chapter 10, section 5. How many different number 17. So this is problem 17 if you want to reference this. So the question they ask is, how many different ways could 3 distinct days of the week be chosen so that at least one of them begins with the letter S? Assuming the order of selection is not important. So if order is not important, is that going to be a combination or a permutation? Combination. Order is not important for combinations. So what you have to do is think about, well, is there any way I can answer this problem without having to answer the original problem, at least? So it says, so what we need to do is pick 3 days of the week. The opposite of at least one is none. Okay, so what we're going to do is we're going to figure out the total number of the total number of subsets of 3 days out of 7. That'll give me the total amount. Then what I do is I found the number of subsets where I have no days that start with an S, because that's the opposite of at least one. At least one means you have 1, 2, 3, 4, but the opposite is none. Okay, so that's what we're going to do. So the total number of ways that 3 days could be chosen from 7 days, there's no restrictions. That's going to give us the list of all of them. So to answer that question, we just say, okay, it's a combination because order is not important, so we use the combination formula. When we choose a day, we can't use it again, so we're not repeating it. So we take 7 things, taken 3 at a time. That'll give us the total number of ways 3 days can be selected without any restriction on those days. So that's going to be 7 factorial divided by 3 factorial times 7 minus 3 factorial, which is 7 factorial divided by 3 factorial times 4 factorial. So we rewrite 7 factorial as 7 times 6 times 5 times 4 factorial. We go down to the largest of the 2 factorials. And then we can cancel those out. And so that leaves us with 7 times 6 times 5 divided by 3 times 2 times 1, which is going to be 35. Now, how did I do that so quickly? Does anybody see where I could simplify this further before I did that calculation? Right, yeah. So 3 times 2 is 6, so I canceled. So I said, oh, it's just 7 times 5. Okay. So that's kind of the universal set. The second one is the number of ways that 3 days could be chosen from days that don't use S, because I said at least one S. So this is the complement. This is asking the complement question. The number of ways that 3 days could be chosen from the 5 non-S days. So that way, we're still choosing 3 days, but we only have 5 days to choose from. So that's going to be 5 factorial divided by 3 factorial times 5 minus 3 factorial. And we do the math in the parentheses first. And in this case, I could just go down to 3 factorial. So it'd be, so it'd be 5 times 4 times 3 factorial divided by 3 factorial times 2 factorial. The 3 factorials cancel out. And the ultimate answer, when I run out of space here, is 10. 5 times 2 is 20, divided by 2 divided by 1 is 20, divided by 2 is 10. Okay, so there are 10 ways that you can take the days that don't use S to find out how many arrangements those are. So then we can take the difference of those is going to answer the question, because I'm going to take the total number, I'm going to subtract the opposite of what they asked, which was this number. So the number of ways that 3 days could be chosen that at least one of the days is a Saturday or Sunday is going to be equal to the total number of ways possible without any restrictions minus the total number of days that don't include S. And so the final answer is 25. Now, how would you do it? Is there a long way of doing it that would give you the same answer using the same idea? And not real, well, you might have to do it with just Saturday, just Sunday, Saturday and Sunday. Yeah, I don't know how you do it, so don't do it. The key thing was that whenever you see the word not or you see at least something, at least usually means that at least means there's more than one possibility. So it's sometimes easier to do the opposite of at least, which usually means none or something like that. Okay, so this is problem number 22. That's to keep you awake there. They automatically, they're yeah, sound like they're about to fall apart when you least expect. Okay, so it says find the number of 4-digit counting numbers containing at least 1 0 under each of the following conditions. So what's the opposite of at least 1? At least 1 0. Well, no zeros. Okay, so the opposite of at least 1 0 is no zeros. So what we'll answer is how many. First thing we're going to do is, and we're going to look at 2 cases where repeated digits are allowed and where repeated digits are not allowed. Now we don't necessarily have to use combinations. We just have to use it to find the answers. So in this case, I don't think we use combinations. We just use the counting principle. So these are the 2 choices. Let me add. We'll do 1 page with repeat digits allowed and where repeat digits are not allowed. Okay, so what we're going to do is do all possibilities. This is the universal set. What does that mean? How many 4-digit numbers. So let's think about this. What do? We have a 4-step process. We're gonna choose the first number. I'm going to use the hashtag as a short thing for number. We're going to have the second number. We're going to have the third number, and I guess that should be third. And we're going to have the fourth number. And then we're going to list the number of possibilities for each number. So if you have a 4-digit number, what are the possibilities for the first digit, this digit right here? How many different options are there? Can't use 0. 9, right? Okay. So you have 9 possibilities for the first one, because if you had 0 for the first one, it would not be a 4-digit number, it would be a 3-digit number. Yeah, so 0 through 320 is the same as 320, so that 0 doesn't count. So that's why you have to do 9. Then your second digit can be, since I'm allowing repeats, 10. And my third digit, they're 10. And my fourth digit, they're 10. If you multiply all this together, you get 9,000. So there are 9,000 4-digit numbers, from 1,000 all the way up to 9,999. If you counted all those, you get 9,000 of them. But we don't want to count them, so we use the fundamental counting principle and ask how many different arrangements are there for each step. So we had 9, 10, 10, 10. So that's the total number. Now it says what we need to do now is figure out the numbers that don't contain zeros, because that's the opposite of containing at least 1 0. Okay, so we'll say, now this is the first step. The second step is number of, I should say quantity, because number, I'll repeat that. Hold on. My cursor has disappeared for a second, so let me see if I can find this thing. It's going to come back, or I'll have to just reset this thing. Looks like I'm going to have to reset it. Okay, we'll say quantity instead of number, since we're talking about numbers. Quantity of 4-digit numbers that don't contain zeros. So that's the opposite of containing at least 1 0. So I do the same thing. I'm going to look at each number, each decade, and ask the question. So we know originally we couldn't let the first number be a 0 anyway, so we're still going to have the same 9 numbers to choose from for the first digit, 1 through 9. But this number 10, I can't use 0. So I make that into 9, because no zeros. I can use all the other numbers, 1 through 9. So the same thing applies to each next step. And so you multiply those together, and you get the total number that don't include 0 at all. And I left my calculator over in the other room. Oh, no, I must have. Okay. Can somebody calculate that for me, please? Say it again. 6,561. Okay. So that's the total number of ones that don't have a 0. So what we can then say is, therefore, the quantity of 4-digit numbers that contain at least one zero is 9,000, the total number, minus the number that don't contain zeros, and that difference is going to be equal to, let's see, it's going to be 3,439. Is that right? Can you check? 2,000. Yeah, right. This is a side light. We talked about this last semester about how to make subtraction into addition. So what you could do is you could say, okay, if I add 2,000 to that, so 2,000, I'll be up to 8,561. Then if I add 400 to that, I'll get to 8,961. And then if I add 30 to that, I'll get 8,991. And then if I add 9 to that, I'll get to 9,000. And if I add all these numbers together, I get 2,439. So it's a different way of doing subtraction by figuring out how I add, and you start each decade and move yourself up there. So anyway, that's a little sidelight about math, mental math. Okay, so that's the answer. So so if you do repeat digits are not allowed, again, you look at all possibilities. And we have 4 steps. So the first step is 9. Now, how many possibilities do I have for the next one? Do I still have 10, or do I have less than 10? So we had, so we're looking at this one. So yeah, we could use any number between, but if let's say we used 9, the number 9, not 9 possibilities, but 9,000, and we can't reuse 9 now. So the 10 would become 9. Okay. And the reason it wasn't 8 was because the fact that we didn't use a 0 here to start with. So that gave us 1 additional possibility. So, and then if we now use two of the numbers and we can't repeat it again, then we only have 8, and then we only have 7 for the final one. So you multiply those together. So Kelly's going to do that for me. All right. Yep, okay. So those are all the possibilities. Then we'll say without 0. So again, the first choice is we already have taken 0 out of that. So the second one, we can't use a 0, and we can't repeat what we did in the first one. So what does this 9 become? 8, because we started with 10. We can't use 0, so that's 9. And we can't use what we used in the first one. So this becomes 8. This becomes 7. This becomes 6. So Kelly's going to do that for me. 3,024. And so the final step is 4-digit numbers with at least 1 0 but no repeats. So since I did these counting with the restriction of no repeats, then I can just take the difference between these two, which would be 1,400 and no, 500, I guess. So if I did this right, 1,512. Is that right? Okay. So 1,512. Again, we didn't use combinations in the case. We used the fundamental counting principle, applying the idea of how many choices do we have in each step. Is the number of choice, we can use the fundamental counting principle if, so Eli's got his class, remember that? It was yesterday in my other class, somebody told me they had to leave early, and then somebody else left. I'm like, where are you going? So if you need to leave early, that's fine. Just let me know. Otherwise, I start to take it personally. So anyway, so we can use the fundamental counting principle if the number of choices for each step is not dependent upon the previous choice. As we've said many times, the previous choice does determine what the options are, but that doesn't affect the number of options. And so that's the same case here. If any number we choose for the previous step doesn't change the number of possibilities. Okay, so here's a couple more problems. If you toss 7 fair coins, in how many ways can you obtain each result? At least 1 head. And it says there, this is problem number 3. This is easier. So at least 1 is the complement of none. So we have to answer, again, we're going to use subtraction to figure out the answer. So the first thing we're going to ask is number of arrangements without restriction. So how many ways can we toss 7 fair coins and get heads and tails? We just did this a minute ago. 2 raised to the what power? 7th power. Because we have a 7-part process. Each process has 2 choices, heads or tails. So each one we multiply 2 by 2 by 2, and the number of tosses is how many times we multiply it. So it's 2 to the 7th power, which is, what is 2 to the 7th power? 128. So there are 128 possibilities without any restrictions. That's our universal set. The second question we will ask is number of arrangements out of this 128 with 0 heads, which is the complement of at least 1 heads. So how many arrangements can we have where we have 0 heads? What is another way of saying 0 heads? 7 tails. Okay, how many ways can we have 7 tails? 1 way. It's the first coin's 7. The first coin's a tails. The second coin's a tail. Third coin is there's only one arrangement out of the 128 that's all tails. So the answer is 1. So the number arranged with 0 heads is 1. It's tails, 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 7 tails. So to answer their question, the final answer, number of arrangements when you flip a coin 7 times, the number of arrangements with at least 1 head is the difference, 128 minus 1. So they're 127. That's a lot easier than, we can't answer this question at least using fundamental counting principles. The only way we could do this is to do a tree diagram and list them all and then look at them and say, okay, which ones, have at least one head. You could count on all 127 of them. But it's a lot easier to use fundamental counting principles to calculate the total number and to calculate the complement, which is no heads, and take the difference. Just like the counting women at a computer science or men at a nail salon or something like that. Okay, so we did the short way. Okay, so then we have, this is number 5, at least 2 tails. So the opposite, or the complement of at least 2 tails would be, let's see if we can think about that. What is the complement of at least 2 tails? Question mark. Well, the answer, I'll tell you the answer, and then we'll do another one so you can. It would be 1 tail or 0 tails. So if we can figure out, this is not, you have to use, there's 2 parts to this, to the complement, but it's still a lot easier than looking at least 2 tails. At least 2 tails, how many would be 2 tails, how many would be 3 tails, how many 4 tails, how many would be 5 tails. And they're actually, going back to this previous problem, there is an actual intermediate that's not completely as complicated. So let's use something we just learned in the previous section. So let's say 0 tails, 1 tail, 2 tails, 3 tails. These are all my options. If I flip a coin 7 times, 4 tails, 5 tails, 6 tails, 7 tails. Because what we were saying earlier was this is 7 things taken 0 at a time, this would be 7 things taken 1 at a time, this would be 7 things taken 2 at a time, 7 things taken 3 at a time, and so forth through this whole different number of tails. And this is equal to 1, this is equal to 1, this is equal to 7, this is equal to 7. The other ones I'm going to have to go into my Pascal's triangle and just write them down. So this would be 21, this would be 21, and the middle is 35. And if you add all these numbers together, you get 128, which is what we got by using the fundamental counting principle. So to figure out at least 1 tail, you would add all these up. And if you add all those up, you get 127. But it's easier to just take the fact that we know the total is 128 and just subtract this one. It gives us the same number. But that would be the long way you would do it. Instead of listing all the possibilities, that would probably be overkill. We have a method of figuring out the individual number for each specific case. So we can use that fact over here, because if we want to find the complement of at least 2 tails, that's 1 tail or 0 tails. So we just figured it out over here. So how many combinations have 1 tail? Somebody read it off there for me. 7, yes. And 0 tails, 1. Okay. So again, what we do is we look at the total number of arrangements, which is 2 to the 7th power, which is 128. And the second thing we do is the number of arrangements with 0 tails or no tails. Well, that's 7 plus 1, which is 8. So to answer our question, the number of arrangements with at least 2 tails is going to be the total number of arrangements minus the complement, so we get 120. The long way would be to go over here and say, well, all of the ones from here downwards have at least 2 tails. This one has 3 tails, which is at least 2. This is 4 tails. So you could add all these up, and you would get 120. Or you can not add them all up, just add these 2 up, and subtract that from the total 128. So that's how those kind of problems work. So we have the, we have how to handle coins. Usually in the test, I do a coin problem. So if you understand what I'm doing right now, you'll be in good shape when it comes to doing these cases of at least something and then going from there. Okay. Then there's a couple more problems where you roll a die. If you roll 2 fair die, say red and green, in how many ways can you obtain each result? So does anybody remember back from section 1 how many possibilities if you roll 2 die? 36, because there's 6 possibilities on the first one and there's 6 on the second one. You multiply that together, you get 36. So what's the so to answer this question, at least 2 on a green die. So what would be the opposite of at least 2? Yeah, so there would be, so let's look at it. We already did the total number, so let's do that. That's 36. That was from the fundamental accounting principle. We take the opposite of at least 2, so the opposite of at least 2 on the green die, that is going to be 1 on the green die. Because you don't have 0. It can be 1, 2, 3, 4, 5, 6. So the opposite of at least 2 is going to be 1. So the question here is the number, what is the number of arrangements with 1 on the green die and any number on the red die. So how many out of the 36 have a 1 on the green die and all the other combinations on the red die? 6. Yeah, you're going to have 1, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. The first number being the green die and the second number being the red die. So there's 6. So that's the complement. So the answer is 6. So to answer the question, number of arrangements with at least 2 on the green die is 36 minus 6, which is 30. I don't know what I did there. And yeah, good. I'm glad I'm recording this. So to give you a little insight in here, Perry McClure High School offers Math 151 and 152 dual enrollment. And it was taught, 151 was taught the first semester by a teacher there, but the teacher is no longer there, so they don't have anybody qualified to teach it. So I'm teaching this, which they will now hear because I'm recording this. I got to make sure I record this so that they can hear it. Hello, people in Perry McClure. They're not actually online right now. They listen to the recording like you did last semester. And that way they can take the class. So what they're doing is watching the class as a class. They have a substitute. They're going to watch the class as a class, and then then they get the homework assignment. And we're going to get together once a week via Collaborate to see if there's any questions. But so I'm not gonna cuss in this class. I'm not gonna say anything too something I wouldn't want high schoolers to hear in this class. I'm not gonna remember to record the thing because if I don't record it, then I'm in trouble. What's that? Yeah, there you go. Okay, so here's another one. The 10 longest Broadway runs include The Phantom of the Opera and Les Miserables. 4 of the 10 are chosen randomly. Assume order is not important. How many ways can the 4 be chosen? How many ways of those groups of 4 would include neither of the 2 productions mentioned, and how many of them would include at least one of the 2 productions? So what this problem is doing is it's trying to answer the last question, but it's leading you through by asking you the 2 previous questions, which is the same 2 questions that we've been asking. What's the total number of arrangements or possibilities or subsets where we don't put any restrictions on it? Then we do the one that's the complement of what we're trying to find out. So here, notice it says at least 1. So the way we would do that is by what are the number of arrangements that don't include either one of them. That's what we'll answer here, and then we'll take the difference between the 2 answers we get in A and B, and that'll answer the last question. So can we use, we can always use the fundamental counting principle. The question is, in this case, can we use either combinations or permutations to answer this? So what are the requirements? What's the difference between combinations and permutations? Yeah, so combinations, the order is not important. And in this case, the order is not, it tells you that an order is not important. So it kind of gives that away. And secondly, for combinations, you don't allow repeats. Okay, so you wouldn't allow repeats. You wouldn't watch Les Mis twice. You could because it's really good, but you probably wouldn't if you were picking 4 different ones. So we can use combinations. So when we answer question A and we use combinations, so here's A. So we have combinations. We just have to figure out what the numbers are. So how many shows can we choose from if there's no restrictions? 10. And how many are we choosing? 4. Okay. So now we just have to evaluate it. 10 factorial over 4 factorial. 10 minus 4 factorial, which is 10 factorial divided by 4 factorial, 6 factorial. And I rewrite 10 as 10 times 9 times 8 times 7 times 6 factorial. I choose the bigger of the 2 so I can get the most bang for my buck here. And So I have 10 times 9 times 8 times 7 divided by 4 times 3 times 2 times 1. And I'm just going to, since I don't have my calculator, I'm going to do as much simplification as I can. So 4 times 2 is 8, so I can cancel those out. And 9 divided by 3 is 3, so I get 210. So there are 210 different 4-show groups that I can come up with. So that's part A. The second one says, how many of these groups of 4 would include neither of the productions mentioned? So now it's still a combination, but how many shows do I have to choose from now? If I had 10, I can't include 2 of them, 8. So, but there's still 4 shows. So that'll be 8 factorial over 4 factorial times 8 minus 4 factorial, which is going to be 8 times 7 times 6 times 5 times 4 factorial divided by 4 factorial times 4 factorial. Those cancel out. I make sure I remember to write 4 factorial out and not just leave it as 4. So we have 4 times 3 times 2 times 1. Again, 4 times 2 is 8, so I can cancel those out. 6 divided by 3 is 2, so I get 70. So there are 70 for part B, and therefore, to answer C, how many of them would include at least one of the 2 productions? Well, that's the number of arrangements where everything is available to choose from, minus the ones that don't include these. So 140, which is kind of surprising, 140 out of the 210 possible have at least Phantom of the Opera and Les Mis. You wouldn't think there would be that many, but it would be that many out of the, it's basically 2/3 of the show. The 2/3 of the choices have at least 2 of the ones, and it doesn't matter, you could pick any 2, whatever the other shows are, would have at least 2 of the, would at least have Phantom of the Opera and Les Miserables. Okay, so that's using the complement. The second one is what's called the additive principle of counting, and it says the number of ways that one or the other of 2 conditions could be satisfied is the number of ways that one of them could be satisfied plus the number of ways the other could be satisfied minus the number of ways they could both be satisfied together. You might think, or you just add them together. But if we look at it from a set perspective, visual, you'll see why that's the case. So back to set theory for you guys who took the first semester. We use this, and remember the union has one or the other. So it's an or statement. So the number of elements that are in set A or in set B is the number of elements in set A plus the number of elements in set B minus the number of elements that are the intersection where they're both. And the reason you have to subtract is if you just add these 2 together, you're double counting certain instances. It says if sets A and B are disjoint, that means there are no common elements between the 2, you can just add them together. There's no relationship. If I said, what's the number of the number of women in this class and the number of chickens in somebody's chicken coop, or in the chicken coop. I mean, they have no relationship, so there's no expectation that they are. There's crossover. But if you said, the number of, if you were talking about classes, you might have this class together, and some of you may share another class. And if we use the or, if we just took the number of people in this class plus the number of people in that class that met a certain qualification, you might be double counting them. So let's look at and this is from a set theory standpoint. What we're talking about is things that belong to set A. So the numbers 1, 2, 3, 4, and 5, and 6 are in set A, and the ones that are in this set J are 5, 6, 7, 8, 9, 10. So the number of arrangements are 6 in set C, and they're 6 in set J. But if you said OR in set C or set J, they're not 12, they're only 10. You can count because this one is in both sets. A lot of these have to do with They use cards as an example because cards can be numbers, but they can also be suits. So there is that commonality. So if a single card is drawn from a standard 52 card deck, in how many ways could it be the following? A club or a jack. Obviously, it can't be a club and a jack, right? So that gets rid of that extra term. So what we do is we ask the question, how many cards are clubs, how many cards are jacks, how many cards are clubs and jacks. So break this up into 4 parts. Number of cards that are jacks. Now, how many people don't know their cards very well? Because that's surprising. It's more than it used to be because people don't play cards. Everybody pretty comfortable with, how many cards in a suit and different kinds of cards. Okay, that's good. So the number of cards that are jacks, not that jack. The number of cards that are jacks. So there are 13 cards. The number of cards I got my numbers wrong. Let's try it again. There are 4 jacks, 1 for each suit. The number of cards that are clubs. There are 13 clubs. We also need to ask the question, number of cards that are clubs and jacks. How many jack of clubs do we have? 1. So to answer the question, how many ways can you have a club or a jack? It's going to be the number of ways that are club plus the number of ways that are jack minus the number of ways club and jack. So we have 13 out of the 52 cards are clubs. 4 out of the 52 cards are jacks. 1 is the jack of clubs, and so there are 16 ways. So the chances, if you going to probability, which is the next chapter, if I said what's the probability of getting a club or a jack? Well, probability is the number of events divided by the total number of possible events. Well, the event is it a club or a jack? So you take 16. The total number of possibilities are the total number of cards, which is 52. So it would be the ratio of those 2 numbers would give you the probability of picking a club or a jack. Okay, what do we got next here? So here we have a group of 30 students enjoy, there's a group of 30 students, 25 enjoy music, 22 enjoy cinema, and 18 enjoy both music and cinema. How many of them enjoy at least one of the 2? We could do this using just looking at it from a Venn diagram standpoint, but we can also do it by using this equation. Okay. So we did this last semester. What we had was 18 enjoyed both, so we have this intersection of the two. And then we said, okay, so that's this little slice. 25 enjoyed cinema, or 22 enjoyed cinema, so this must be cinema. So 4 plus 18 has to be equal to 22, because that's the total number in that circle. This football is where they both enjoy it. And then 25 enjoy music, so this must be the music circle. So if we have 18 here, to get 25, we need to put 7 in there. If you add those three together, you don't get 30, so there's one person that apparently doesn't like movies or music. Must be a boring life. So then, how many of them enjoy at least one of the two? So at least one of the two is an or statement. It means they like music, they like cinema, or they like cinema or music. It's basically the question they're asking is an or question. So instead of asking how many of them enjoy at least one of the two, you could also ask the question, how many of them like music or cinema? So to answer the or question, you would say, how many like music? I'll put a little n here. The number that like music, the number that like cinema, minus the number that like music and cinema. So from the problem statement, 25 enjoy music, 22 enjoy cinema, 18 enjoy cinema and music, and if you do that, you will get 29, which you get by just adding the numbers 4 plus 18 plus 7 give you 29. But this is the way you would do it in terms of using the whatever they call this. What was the name of this? The additive principle of counting. Okay. So I'm going to assign I'm going to assign the homework from this section today. So it's due next Tuesday. I think we'll stop there. We just got a few slides left. We'll do that on Thursday, and then we'll move on to chapter 11, which is probability, which is basically using counting principles and then taking ratios of numbers to come up with probabilities. And we'll answer that burning question of what's the probability of an 80% free throw shooter of making all 3 shots at the end of a game, as long as he doesn't get nervous. It should affect his, he doesn't choke. I'm a reasonably good free throw shooter, but I found out that it's kind of like playing golf. The more you try to get that little extra bit, the worse it happens. So you get to this point where, I can shoot, if I don't worry about it too much, I can shoot 80 to 90% free throws. But trying to get above 90%, then you start to think really hard about what you're doing, and thinking too hard messes you up, and you actually go the other direction. You've got to get to the point where it's automatic, and you kind of accept that you're not going to get every one of them because of